Hi everybody. This is for MTH 346. Welcome again, back to the whiteboard. I wanted to give a quick example of using the basic form of Ito's Lemma. So remember, if we had a basic Wiener process, right? So we had something like dx is equal to, right, that's sort of our mathematical formalism for a basic Wiener process. And then we had, say, some y, which is g of x, right? Now these are functions of t. I kind of ignored the t here, right? But it's y of t and x of t. And so it's a function, right? So we're taking x and we're putting it through something. So x is just this kind of noisy stuff. And we're going to plug it in and put it through some function, right? And so in that case, we have Ito's lemma. The basic form says that, hey, dy is going to be 1/2 the second derivative of g, right, with respect to x squared, and that's going to be dt. It had this sort of drift component, right? Drift component plus dg dx times dx. So this is our drift. You can think of it as like a sort of a convexity effect due to the convexity of the function g, right? And so it forces that process to have some drift, and we'll give an example of this in the next video when I show you some things on MATLAB. And this here is just the original Wiener process, but it's multiplied by the derivative. So if the derivative is positive and say high, meaning steep, right, you're amplifying, right? You're kind of amplifying the dx, right? It's making it noisier, if you will. And so that's our sort of basic form of Ito's lemma. We're going to get into the more general form of Ito's lemma when we start lecturing again. But I just wanted to give you an example. So let's say we have y of t is equal to x of t to the n. Now let's just say n is greater than or equal to 1. Okay, so we're just raising x of t to some power, right? Squaring it, whatever. And so what do we have? We have dropping the t, right? Dropping the t, we just look at dy dx, and of course we all know what this stuff is. N times x to the n minus 1, and then of course d squared y dx squared is just n times n minus 1 x to the n minus 2. And so just basic calculus. And so we can write, right, dy, this is the process, right, dy is going to be 1/2 n times n minus 1 to x to the n minus 2 dt, right? So this whole thing is going to be my sort of drift component, dt plus n x to the n minus 1 times dx. So you've got this drift component here, and then you've got this random component which gets multiplied by whatever the value of x is at that time, right? Of course, everything is an infinitesimal time anyway here, right? And so we'd like to sort of resubstitute back in and make this formula in terms of y as opposed to x's here. And so we would write, we could obviously solve this over here, right? And we can say that x of t is going to be y of t to the 1/n. So we can write this as dy is equal to 1/2 n times n minus 1, whatever that is. Put in 1/n there, and I'm going to get y to the n minus 2 over n, right? And dt. Right, so now I've got everything written in terms of y, and then this would be plus n times n minus 1 over n times So I just wrote it down as basically a stochastic differential equation where we're driving it by the random disturbances. Remember, that's dx. So if you did a dy dt here, which, right, a dy dt, you'd have this constant plus this constant times dx dt, right? And we already said last lecture, dx dt, what is it? It's that Gaussian process, white Gaussian process. So it's like taking a random Gaussian variable at every instant of time, and you're perturbing this equation by that amount. Right? So it's kind of like, it's, you know, we refer to it as stochastic differential equation. Right? This is the differential form of that. So this would be like an SDE, stochastic differential equation. Right? Exciting stuff, this stuff, right? If differential equations weren't bad enough, now you got stochastic differential equations. Right? So just notice here, n equals 1. N equals 1. Notice this will be 0. So what do I have? I have just dy, n is equal to 1. This will be 0. Y to the 0, that's 1. That's 1 is just equal to dx. Okay, it makes sense because we're saying y is just equal to x. Okay, and n equals 2. And so n equals 1, we had this. N equals 2, what do we get? We get dy is equal to, put the 2 in here, cancels this stuff out. 2 minus 2 is 0. It's just going to be dt, right? It's going to be dt plus 2y, I'm going to put the 1/2 dx. That's right, equal to. So we could say, I mean, right, we could say for small, right, we could say that, right, for small, right, if you want to say small t, that y t plus, say, tau minus y of t, right, is approximately equal to just tau, right, the difference in time, plus 2 times whatever y of t was, say to the 1/2, times x of t plus tau minus x of t. But remember, what is this? This is just a normal random variable 0 square root of tau. Right? That's just a normal random variable 0 square root of tau. Right? So if we wanted to, right, we could say that, hey, y of t plus tau is approximately normal, right, with mean y of t plus tau. That's not in the subscript there, it's y of t plus tau. So that would be plus tau. And it would have variance, or standard deviation, would be 2 yt to the 1/2 times square root t, tau, square root tau. Right? So given what the initial value is y of t, we can then make statements about what y of t plus tau is. Right? What y of t plus tau is. So while it may not be, when you have a transformation, obviously, if this is sort of a normal random walk and you're squaring it, right, you're not going to get a normal random walk. Like a normal random variable squared is a chi-squared, right? So, you're not going to get sort of a normal distribution anymore, but you can say, hey, small tau, you can approximate that normal distribution. So anyway, that's one way to do, using Ito's lemma, right? And we'll get more into this when we get back. But I just wanted to kind of give you that little bit of review on Ito's lemma. All right, I'll be back with some MATLAB discussion.